and welcome. We are underway looking at the numerical solution of ordinary differential equations. So we have seen yesterday Euler's method, and we have already seen which is first order, and we have already seen the second order method, that is Poincare method. And here you have the information that the demo material that Reda gave on Tuesday is out, so you can look at it. Those who were present, you know what it is about. For the others who were not there, you can have a look at it, and then you can see how you can solve ODEs. So the codes that are available, the programs, the scripts that are available are for computing the machine epsilon that we discussed. So that is the smallest number. When you add it to 1, that gives something larger than 1. Below epsilon, the computer doesn't see it. And then these are examples to compute the orbit of a planet around the Sun using different methods. Euler, that we saw yesterday, Point, that we also saw yesterday, and this method that we shall have an idea, that you shall get an idea on in a minute, what this is about. It's ODE 45. That's an inbuilt function in MATLAB, so that you can use. For the others, you have to do the programming all yourself, but for ODE 45, you can use this. So then you can see how these work. And I'll show also something about that later on. And what is very interesting and useful, not only when you use ODE 45, is to define the right-hand side of the ODE, what we call f of ty. That is called here func point m. So you define this, usually it's a vector, if you have a system there, so that it can be used by, for example, ODE 45. But you can also use it when you do the programming yourself. Okay, so regarding your background, do you know the classical Runge-Kutta method? Please raise your hand. Okay, very good. So that will be just a repetition. By the way, which book have you been using in Calculus 4? Kreisig. Okay, so then this is what is coming now. It's just a repetition. But anyway, I think it's important so that you see it again. That is our example 2. That is the classical fourth order Runge-Kutta method. And it is used quite a lot because it will give us, as we see here already, fourth order accuracy. We can use the acronym RK4. We have seen in the Euler method we have one function evaluation, and in Point we have two function evaluations. So that is the costly part. And here in this method we have 4. So the first one is just the same as we have with the explicit Euler method and also with Point. So that is just to compute the right-hand side of the ODE f at the old time level that we know and at the solution at the old time level that we already have. And then we go now the following way, that we take the time level at hn half. So hn is the step size, time step from tn to tn plus 1. And we go actually half, and then we take the old solution yn, and we go there by computing hn half and using the function that we have already computed here. So this is, in a way, you could imagine it would be, if we just look at this, it would just be an Euler step going to hn half, not to hn. But the point is that we can use now these slopes, because the f's are the slopes, in each stage from the previous. We call this stages. So then the third one is very similar. You also go to hn half, and And now we take the yn, again, hn half, and now we take the k2, the most recent slope. And the final stage, k4, is we do the function evaluation now at tn plus hn, and then we take here the yn plus, we go the full time step to the next level with hn, and we take the k3. So then we have 4 slopes, and then we do clever averaging that was then devised by Runge-Kutta, and that is that we use yn plus 1, that is our solution at the new time level. We have then the solution at the old one, plus the time step hn divided by 6. And then we have the following averaging, k1 plus 2k2 plus 2k3 plus k4. So that is then the result. And that gives us then the solution at the new time level, n plus 1. So we go in, it's a one-step method. We go from time level n to time level n plus 1, but we need 4 stages to get these different slopes. That gives us then the high order. So I will call this here, give it number 10. So all this together, that would be then the 4th order classical Runge pattern method. The local truncation error can be shown, but it's rather tedious to do. I did it once. Is that we can expect if we have a 4th order method, local truncation error must be 1 order higher. So it must be 4th order. So the En, as we call the local truncation error, is of the order h to the power 5. And that means then that the global error, which we call capital En, is then of order h to the power 4. So that means that we have here 4th order. 4th order accuracy. And that makes this method really attractive. For when we compute a solution with a time level h, with a grid spacing, h, and then we do take h half, the error will go down quite a lot. So let's see that. So if we write now the global error in this form, we can essentially write it as some constant k times h to the power 4. So I write this, it's not really exact because the constant usually depends also in a way on the h a little bit, it's around x somewhere, but it's essentially like that. So then you can imagine when we do then take the half of this time step h, that we get then something, we use the same constant, but then we get h half to the power 4. And that is equal to the error that we had already before. I write it in this form, divided by 2 to the power 4, which is 16. So this is then essentially equal, if we use again this here, the error that we had with time step h divided by 16. So that means the error, the global error, is reduced by a factor of 16. Compare that with Euler's method, the error is only halved. With Heun's, quartered. But here, the error is only 1/16. So that is very, very good property of the method, that the global error gets low very quickly as you refine the time step. So that makes this then really attractive. And Runge-Kutta methods have attracted CFD quite a lot. And the reason is, one is, for example, this method because of its accuracy, but another reason is its simplicity. Because if you think of it, what we are going to do is we are going to do a space discretization. That is coming soon. And then we get a system of ordinary differential equations. So in our case, we have a system. And the number depends on the number of grid points that we use. It can be billions nowadays. And it depends on the number of equations that we have. So we get a large system of ordinary differential equations. So our system, our F is then really big. And then it takes a lot of time to compute then our F. The Y is then our vector of all unknowns, so billions of unknowns. And to compute this F is very costly. And in that case, we have to do it 4 times. And each time we compute that, we have to go to a lot of machinery, a lot of functions or subroutines. But if you do that once, then you can reuse it. Every stage you can reuse it. You just feed your function with new values of the time that you are and new values of the approximation of the solution that you are. So here you use Tn, Yn, here you use this, and so on. So you need only one essentially set of subroutines for computing the F. And then you just call it in this fashion. And this you can write also in MATLAB, also in other higher languages, just as it is here in 5 lines. These 4 slopes and this. That's all. So it's very neat and very useful. So that is that regarding Runge-Kutta method. There are a lot of others that we don't go into. In the book that I mentioned by Haira Nosservana, and also by the second volume, Haira Vanna, you find a lot of other methods. And in CFD, they have often been tuned to have certain properties. That they have good stability properties might be more important than having high accuracy. So then accuracy is lowered, but stability is increased by choosing these coefficients in an appropriate way. And one example of where this has been done is actually ODE 45. And that is coming from the ODE community, people in numerical analysis, like here at NTNU, who are specialized on numerical solution of ODEs. So that brings us to a step that is also built in this ODE 45, that is an automatic step size control. So I want to give you an idea of that. It is not important to understand everything, especially the method, ODE 45, I don't go into detail in that, but the idea behind it. So, and the example that we want to, what gave us discussion, or the goal of the discussion, is this ODE 45 in MATLAB. That uses a method which is called Dormand. These are the people who devised this method, Dormand and Prince. Dormand and Prince method. And that method is also a Runge-Kutta method, but it is a 7-stage Runge-Kutta method. So we have 7 functional evaluations, but they do a little trick. They only need 6 in the end. But it is a 7-stage Runge-Kutta method. So we use this name Runge-Kutta not only for the classical one, but also for others. And that yields actually two solutions. Two solutions. And I want to denote them by yn. So we have the index below. The yn is, that is the first one, and the second one, yn. So we get two solutions. So, and the trick with that is the following. They have the following property, that the first one, if we look at the global error of that, no, we look at the local error, sorry, the local truncation error, because that is the one that we really can control easily by using Taylor expansion. We get then the solution of this ODE problem, which I denoted by un-1. That means we start at the time level n-1 with the numerical solution there, and then we go to the time level tn. So then we get that. So what I write here is to get the local truncation error. So that is then the local truncation error of the first solution. And similarly, we get then the solution for the second. Then we get there another truncation error, which you note, local truncation error, which we note by en2. And the catch is that these are of different order. So with the local truncation error, of the following, the en1 is of order h to the power 5. So that's the same as the classical Runge-Kutta method. But the second one is one order higher, so it's more accurate. And with that, we can compute the difference and get actually an approximation of the local truncation error. That's the catch. So from that, we take simply the difference between these two here. We get then the local truncation error of the, say, the first method is equal to the approximation by the first method minus the approximation by the second method plus the EH to the power, the EN, the local truncation error of the second method. And this now is, as we saw, order h to the power 6. So that means what we do then is we approximate this. So we use then the approximation that we can approximate the local truncation error of the first method by simply the difference of the two solutions. So then we shall use this. And then we have an important information. Then we have a clue what is the error that we do in that case from time level n-1 to n. And that we shall use to determine the time step. That's the idea. So that means that the difference of the two solutions yields approximation of the local truncation error, which is fifth order, that is, as we saw, we'll call it, we'll introduce now an abbreviation for the absolute value of this local truncation error. So that is En1 is then the approximately the difference between the two solutions. So that is the point. So when we have this error, we know it is of fifth order. So that is what we had here. So this, we know that the truncation, local truncation error of the first solution is of fifth order. So we use that now to determine a time step. We want to determine in such a way that we match a certain tolerance. So you will see in the example by radar that using the standard tolerance for ODE45 did not work well for this computation of the planet around the sun. So one had to change that. So then we have, we know that the local truncation error is essentially some constant, I call it now C, h to the power 5. And since we have now an approximation of that, we can compute that, and we know h that we have used, so we have already used some h when we start with it. That allows us to compute the C. So from that we can compute the C. So we do this control after we have done the time step. So we choose one in the beginning, say the one that we used in the beginning, or the time step before, and then we check whether it was okay or not. And that is what we are doing now. So let's first compute the constant C from that. So we get the En1 divided by h to the power 5. And that is then, according to what we have said there, approximately equal to the difference of the two solutions given to us by the Dormand-Prince method. And that is what we call essentially that is the error divided by the h to the power 5. So that is what we get from having two solutions, that we get an estimation of the local truncation error, and by that we get the constant that relates the truncation error to h to the power 5. But what we want is, we want to have a certain tolerance in which our solution lies, certain error tolerance. And that is called TOL, or we call it like that. And if we want to relate that to the time step, then it should also be related to that. If you use this method, say the first method, it should also be related in a similar way as the solution to the first method, or as the first method. So we want to have it in such a form that we have the same constant, and then we have here a new time step, h nu to the power 5. So what we get here is the error that the method gives us. But what we want is we want to have that this error should be equal or close to the tolerance that we target. So then we assume that we have the same functional relationship, and then we can use the C in here to determine the h nu. So we give the tolerance, we say we want this accuracy 10 to the minus 8 or whatever we like, and then we have the C by that, and then we see what is then the h nu that will give us this tolerance, this error tolerance. So then we insert the C that we have here into this equation for the tolerance. And we get then that the tolerance is equal to, if you look at, we take this as the simplest way to express it, so it's then the error, local truncation error, divided by h to the power 5. So that we can insert for that. And then we get that this is equal then to the error. Then we can express the rest, h nu divided by h to the power 5. And from that, we get then the h nu, the time step size that will give us this tolerance. That is then equal to h. We take 1 over 5 to the power 1 over 5, and here we get then the tolerance divided by the error 1 over 5. So then we have it, and then it is just a matter of checking whether this new time step size is smaller or larger than the time step size that we have chosen in the beginning. So we compare then the h nu to the h. And another thing is that we usually do not use it in this way, but we use the so-called safety factors. Because we're doing approximations all the way using safety factors. So, and then in the book by Haira Nasset-Wanner, I found this one. It is h times, and then they take here the minimum of maximum safety factor, and then they take here the maximum. This is a little technical here, but just to tell you what is used. And then we have here the tolerance divided by the error to the power 1 over 5. So then the maximum is closed here, and the minimum is closed here. And what they give a few numbers, for example, as examples of these factors. One could use, they give some range, say 1.5 to 5. And for this they give also some ranges. I just picked here a few numbers. And here I just thought myself what we could do. Usually if you do it in steps of 2, that is not so uncommon, might be different, but these are just an example. And now, if the error that we get from this, or we can compute then the error, let's see, yeah, we have that already here. So then, if we would find out that from the very beginning that it is smaller than the tolerance, then we wouldn't need to do that, or we could do it and increase the time step. But the point is, if the error that we have computed by the difference of the two solutions is larger than the tolerance, then we would have to redo the time step. So that is the interesting one. If the error is larger than the tolerance, then the solutions that we have computed with the time step h, that is yn1 and yn2, they are rejected. And new solutions, these similar ones, yn1 and yn2, are computed with h nu. Are computed with h nu. So that is then, and that can be done again. So if you find that when we have done that, have taken the h nu, of course we have then chosen here, for example, we have just halved at most, might not be good enough, so we might have to redo that. But this gives us then some assurance that we get a local truncation error that is within this range of the tolerance. If you don't do that, usually you choose a time step just by guessing, you might be wrong. So this gives some error control. So that's the good thing. And that is then built in the ODE 45.
Excuse me?
Yes?
Is the tolerance a fixed number?
For ODE 45, there is some default. Yes. I tried to find it out. I think it was difficult to find it, but I think I found it was the relative tolerance, I think it was 10 to the minus 3, and the absolute 10 to the minus 6.
Okay.
But it turned out, and we can see that in the example, that it was not good enough for the orbit. And radar showed that on Tuesday, so then the accuracy was simply not high enough. So that can be a problem. So then one would have to, in that case it was necessary simply to reduce the tolerance. So let me show you that. So, let's see now. Okay, so let's see it. So you have the ones by radar are called Planet. I want to now run similar ones, which I call Orbit. So let's see. So now it's different methods are used. So let's see what happens here. Here are two figures. We start with the first one first. So this is the orbit computed by Euler, by Euler's method. What we have here, the problem is that we have a planet that is starting here. Here we have the sun. And then we are supposed, in that case, to get an ellipse. So it's supposed to come back to the origin if we would have a really correct method. Of course, that is what we should get. But Euler's method, due to the numerical error, it spirals out. So at some point we will leave the solar system with that map. So that is really not good. Another way to view this problem is by looking at the energy. The energy is the kinetic and the potential energy. And in that case it turns out that this is by no means constant. So it should be constant, but you get here really quite a big increase actually. That is not so important, but that it doesn't stay constant, that is the problem. So this does not work really very well. And I've given also two other informations here, or let it MATLAB give that. And that is, here we have the energy variation, so the maximum and minimum of that. It is a measure of the error that we get with the method. And this is the elapsed time. If you write tick in front of a command and toc behind, or a set of commands, you get the time it takes MATLAB to do these commands. So and here it was done before the time loop of the ODE solution. So then we have a measure here that the Euler's method took about 1/3 of a second. So now we want to see how this works with the Hoyne. And well, if we look already just here, before we had here quite a big number for the error, for the energy, which is now much lower. Here we see it is still increasing, but at a much lower level. And the solution looks like this. So it's much better than Euler. It's still not perfect because it should be on one line. Here we see it comes back almost to the same point where it started, but here we see it's drifting a little bit. So, but it's a considerable improvement compared to Euler. Now, if we take now the Runge-Kutta 4, we get this. So, and before we had 10 to the minus 2 with Hoyne, now we have here 10 to the minus 6. So the error is reduced quite a lot. It's still not perfectly constant, but you see here the scale doesn't change, so it's a very low scale. And the solution, let's see, that is now quite good. So we can, there is a little overlap. It may be getting a little thicker here, but it's a very good solution. So then, now how does ODE 45 do that? So ODE 45, and I took now the default as the first option. So you see here, we have still some error here. So the energy is not constant, and the solution is not so good actually. So it's drifting also here. So therefore the radar chose different parameters for the tolerance. So I think it was increased to 10 to the minus 8 for the absolute tolerance, for the relative tolerance, 10 to the minus 10 for the absolute tolerance. And then we get this. So now the error here, if you look at that, is order 10 to the minus 7. Still, so it's very small, and the solution looks very good. So then you can see that these tolerances play an important role, and also the order of the method, but even more some properties of the method. The method need not be great, but it should have the property, in that case, to conserve the energy. So there are methods who do that, who are used, and Reda mentioned the Sturmer-Verde method, which has this property. So then we have to look into this also in these properties of the different methods, how well they preserve certain quantities. In this case, it would be the energy. Okay. So that was what I wanted to show you, and you can play with that yourself by using the scripts that Radar put on the home page. The next thing is, we can slowly start with it already, or I tell you about it first, is stability. So I want to discuss with you stability of ODEs. So that is what we have now seen, that was focusing mostly on accuracy, but there is also the issue of stability. So the stability is related to two things. One is the stability of the ODE, and what we are mostly concerned is with the stability of the numerical solution. But to have an idea, we shall first look at the stability of an ODE. What we want is that a solution to an ODE, if we start from, say, two initial conditions that are close to each other, that also the solution to the ODE should be close to each other. So that is related to what we discussed when we talked about well-posed partial differential equations. So this continuous dependence on the initial and boundary conditions. Here we have initial conditions. So that is then looking at the stability of an ODE. Well, have you seen that before? Stability of ODE. Okay, then it's something new, that's good. So I think that now we can take a break, but I would like to ask you to have the break only 10 minutes, because that we can finish 5 minutes before 10 to allow the people from marine technology to get back to Tyholt. By the way, who of you is from marine technology? Okay, very good. Okay, and the others, who is from PUP? Okay, very good. And energy and environmental science? Okay, fine. And we have some others, I know, from physics, mathematical physics, and others. Very good. Okay, then 10 minutes. I hope that is fine also with the others.